in week 2, right? So when we first talk about complexity. And at that point of time, I was just trying to illustrate to you that there are different complexity classes, and these different complexity classes are very different from one another. So this is a log scale, meaning that every time you go up by 1 unit, you multiply by 10. So which means that we look at the growth, and some of the complexity classes are growing very fast. For example, factorial and exponential. All right, now, if you see this in a different way, if you look at this table, if you have a problem or if you have an algorithm that is exponential, which is 2 to the power of n, or factorial, which is n factorial, then the problem sizes that you can do are very, very small. Now, to some extent, we are actually drawing a boundary here. Okay, because we realize that anything that is exponential and factorial, even if we know an algorithm to solve the problem, but if it is going to take exponential time or factorial time, is as good as not having a solution, because you cannot actually run it properly, okay, except for very small input sizes. So that is essentially what we mean by the limit of computation. We hit a wall. So the current computational capabilities of the computers today, we can pretty much solve all problems that can still run in polynomial time. But once we get to exponential, we cannot. Okay, it means that the algorithm is going to take too long. Now, that takes us to essentially a binary sense of what algorithms are efficient and what algorithms are not. Okay, so now we say that an algorithm is efficient if it has polynomial complexity or lower. Now, if it is at least exponential or factorial, then it's considered inefficient. Inefficient is not exactly useless, okay, but it's close to that. Okay? It's useful if your problem size is small. But once it grows a little bit bigger, then it's useless. You cannot actually run it. Now, which means that in the class of problems, we can split our problems into 2 classes. So we say that a problem is solvable. That means there is a problem. We can solve this problem as long as there is a known algorithm that has polynomial time. Now, if for a particular problem, there is no known algorithm that is polynomial time, then we consider the problem to be intractable. Intractable means unsolvable. It means too difficult to solve. Okay? Now, for such problems, then we come to heuristics. Because we realize that for these problems, they are too hard, they are intractable, they are unsolvable, so we cannot solve them directly. So then what do? We approximate. So we try to get a lower solution that is still going to be good enough for us. Okay? Now, let's talk about some example problems. Now, you need to watch out for this concept, okay? So I'm going to bring in the concept of there is a difference when you try to verify a solution and when you try to derive a solution. These two are different things. They have different complexities. Now, for example, if I tell you there is a 3 and a 5, multiply them. What is the number? The number is 15. Okay? Now, this is easy. All right? So, more or less, it's easy to do. It's going to be O1. Now, but if we tell you there is a number 15, what are the factors? Then it's actually a lot more difficult, because then you have to derive a way to actually do this. Now, for 15, it's relatively simple. You can still do it. But think of having a very big number. Now, if I have 2 large prime numbers, multiplying them, we can still do it. It's still not a problem. Okay? It's just going to take us a bit more time, but we can do it. But the other way around, if you try to go from here to the other side, what is this number? This is actually very difficult. Okay? Now, if you're going to brute force it, it's going to take 2,000 CPU years. Which means that if you use 2,000 CPUs, it takes you 1 year. If you use 1 CPU, it's going to take you 2,000 years. So it's not practical. Okay? Now, but you realize here that there is a difference here, in the sense that if I ask you, what are the factors, it's difficult to get. But if I propose a solution, if I say that, maybe these 2 are the factors, are they the correct solution? You can verify it. Just multiply them and check. Okay? Now, this notion of checking versus deriving is what we are going to talk about next. Okay? So let's say you're given another problem, which is what we call subset sum problem. And the idea is that you are given a set of numbers, and we want to know, are there a subset of them that if we sum them together, you're going to get 0. Okay, now, the brute force way is that we're going to try all possible subsets, right? And because this is a set of n numbers, how many possible subsets? It's going to be 2 to the power of n. Why? Because every element may belong or do not belong to the subset, so there are always 2 possibilities for each element. So it will be 2 times 2 times 2 times 2 n times is 2 to the power of n. Okay? Now, but if I propose a solution, you will be able to check immediately whether the solution is correct or not. So if I say, is 11 5 minus 3? Then all you need to do, sum them up, wrong, right? But if I say, okay, now is 5 minus 3 minus 2? Then yes, you can check 5 plus minus 3 plus minus 2 is indeed 0. So verifying a solution is easy. Deriving a solution is much more difficult. Okay? Now that is the concept that we need to define the next part, which is what are the different problem classes in computing. Okay? Now we say that a problem is in P. So P stands for polynomial if we know how to solve the problem. Okay? Not just we. What I mean is that the world knows there is an algorithm that can solve the problem in polynomial time. So we consider the problem in P. So which means that if you face such a problem, then all you need to do is just to find one of the algorithms that solve the problem, and then you can use it to solve that problem. Now, but there are other problems that we call NP. So NP is non-deterministic polynomial. So it simply means that we can verify it in polynomial time. If I propose a solution, you can check whether the solution is correct. Now, give you an example, like the previous one. If you propose a solution, 5 minus 3 minus 2, you can verify it in polynomial time whether it's correct, just by summing them up together. So summing them up together, in the worst case, you only have n numbers, sum, O(n), you can verify whether it's correct or not. So now, this is P and NP, okay? Now, so remember that P, polynomial class, if there is a known polynomial time algorithm to solve it. Now, for NP is non-deterministic polynomial. It means that there is a known algorithm to verify it. Okay, not necessarily to solve, but it can be verified. So now we have P and NP. Okay, so when you read textbooks and then they say this problem is in P, it means that it's solvable. If they say this is in NP, that means that it's verifiable. And you realize that everything that is solvable is verifiable, because one way to verify is to solve it first. Okay? Now, we are going to go on to the next one. Okay? This next one is going to be a bit more complicated. The third class is what we call NP complete. Okay? So this is a part of NP. But it's not just any problem in NP. These are the hardest problems in NP. All the problems that are verifiable can be reduced into one of these problems. Okay, I will introduce to you what is the notion of reduce. Okay, but the idea is that I can express every other problem in NP in terms of one of these problems. And if we can find a solution to any one of them, we can find a solution to all of them. So essentially, they have identified a set of problems that are the hardest problems, that we can solve them. We can solve all the verifiable problems. And until now, there are still problems that we cannot solve. Okay? Now, in order to define this, I'm going to introduce you the notion of reduction. Okay? Now, the idea of reduction actually is intuitive. So sometimes you have a problem, though you don't quite know how to solve it, but you can transform it into a different problem that you know how to solve. So you can solve the first problem by solving the second problem. Now, let's look at an example. Okay? Now, let's say we end up with two problems. The first problem is that we want to sort an array of integers. Okay? So given an array, they are integer values. We want to sort them, let's say, in ascending order. Now, there is a second problem, which is a different problem, which is topological sorting. So topological sorting is that given a graph, we are going to find topological ordering. Now, we will show that we can reduce the problem 1 into problem 2. So when we say reduce, it means that we are going to express problem 1 as a special instance, as a special case of the problem 2. Now, if it is a special case, it means that problem 2, any algorithm for problem 2 will also solve problem 1. Okay, now let's see how it can be done. Now let's say you have an array, it's 2, 1, 4, 3, and you want to sort this. And let's say you don't know about insertion sort, you don't know about merge sort, you don't know about any other sorting algorithms, but you know about topological sorting. So now you realize that there is a way for us to transform the problem into topological sorting. How? Now topological sorting is going to take in a graph. So then if we have an array, the first thing we're going to do is to construct a graph. So what kind of graph is it? So every number that we are going to sort, we are going to create a vertex. So now that is going to give us n vertices corresponding to every number. Now, and then we are going to complete the graph by drawing an edge from one vertex to another vertex if the first one is smaller than the second one. Now, for example, 2, 1, 4, 3, we are going to create 4 vertices, and then we are going to draw an edge from vertex 1 to vertex 2 if 1 is smaller than 2. So in that case, we are going to draw from 1 to 2, 1 to 3, 1 to 4, 2 to 3, 2 to 4, and then 3 to 4. Now, we do not have an edge from 2 to 1 because 2 is not smaller than 1. Now, so at the end of the day, we have a graph. And then, if we solve topological sorting on this graph, what are we going to get? We are going to get the sorting order of the integers. Now, is there any instance of the integer sorting that you cannot do this process for? For every single one, you can do the transformation. And once you have done the transformation, the more general problem, which is topological sorting, can solve the more specific problem, which is the integer sorting. Okay? Now, this has two implications. The first implication is that it means that the more general problem, it will be harder than the simpler problem. Right? So now you know that integer sorting is n log n. Now, because this is a more general problem, it can solve all your specific problems, but it also has to solve other problems. That means it's at least as hard, at least as complex as the simpler problem. And it turns out that it's actually n squared, because you realize that the transformation itself is n squared. How do we get n squared? Because we're going to create the edges. So now there are going to be n vertices, and from the smallest number, they're going to be n minus 1 edges. From the second number, they're going to be n minus 2 edges. From the third smallest number, they're going to be n minus 3 edges, n minus 4, all the way to 1. So the total number of edges we need to create is going to be in the order of n squared. So the transformation alone is already n squared. Then plus whatever you need to do for the topological sorting algorithm. Okay? Now that's one implication. The more general problem is going to be harder, more complex. The second implication is that any algorithm that solves the more general problem will also solve your more specific problem. Now this gives you a way to see two things. Okay? One, sometimes if you have a problem that you don't know how to solve, one trick that you can do is that you try to transform it into another problem that you know how to solve. Then you can use the algorithm that you know to solve that problem. Okay? Now the second thing is that sometimes you want to know what is the complexity of a particular problem. Now if you can show that there is a more specific problem, and the specific problem already has a complexity of n log n, then you know that topological sorting cannot be lower than n log n. Okay, because it's a more general problem. So it must be at least as hard as a more specific problem. Okay? Now, I gave another example in the slides for the reduction. This one is a more complex example. Okay? But I will go through it, okay? Because I think you know already part of it. Now, I'm going to contrast two problems. One is what you already know, which is a traveling salesman problem. Now, there is a simpler problem, which is what is called Hamiltonian cycle problem. The idea is that given a graph, we just want to know whether there exists a cycle. The answer is yes or no. Okay, does exist a cycle here? Now, a cycle that visits every node of the graph exactly once. So given a graph, we want to know whether there is a cycle that visits everything exactly once. Meaning you don't revisit the same node twice. We just want to know the answer, yes or no. Now, we are going to do this by transforming the first graph into the second graph. Okay, so let me show just a simple example. Okay. Now let's say that we have two possible graphs. So we have two graphs, okay? Let's call them G1 and G2. Now let's say this graph has the following 4 edges, okay? And this graph has the following 4 edges. Now we know that if you want to know is there a cycle that is going to cover all the edges, all the vertices exactly once, we know that in this case yes, we know that in this case no, right? Here there is no cycle that covers all the vertices exactly once. There is a small cycle here, which is BCD, but it doesn't cover A. So we know the answer, okay? But now we want to see, can we solve the problem by mapping it to the Traveling-Saltzman problem? And it turns out that it can be done. And the way we do that is that we are going to transform this into the input to the Traveling-Saltzman problem. And what is the input to the Traveling-Saltzman problem? Is all possible pairs of edges and the distances. There's a notion of distance. So now what we're going to do first is that for every edge here, we're going to put a distance there. And let's say we're going to put 1 on all of them. Okay? So initially there was no distance. Okay? Now, and the second thing that we are going to do is that we are going to make them a complete graph. Complete graph because there are some edges that are missing here. So for example, these two are missing. In this case, these two are missing. Now these are fake edges, okay? They didn't exist before, we add them in. Now, and then we're going to give them a weight of 2. Now, in this case, now this can be then the input to the Traveling-Saltzman problem, because now essentially what we have done is that we are given a set of cities, and we are given all the pairwise distances between any pair of cities. Okay, now let's say that we try to find what is the shortest possible tour that visits everything exactly once. Okay, now which one is it? So for example here, what is the tour? So the minimal tour is going to be A, B, C, D. So we have A, B, C, D back to A, right? And what is the total distance? Is going to be 4. Now in this case, we see that what is the shortest tour is also A, B, C, D. What is the total distance? 5. Because it's 1, 1, 1, 2. Okay? Now, just by looking at this, if there is a distance of 4, it means that there is a cycle. And the reason why there must be a cycle is because all the original edges has a weight of 1. And any cycle that will contain n cities must have n edges. And if all the n edges are original edges, they all have a weight of 1. So then the total distance will be n. Now, if you cannot find, if the shortest possible tour is still larger than n, it means that you must borrow one of the fake edges to create the tour. So it means that you don't have enough original edges by itself to have a cycle. Okay? Now, this one, I understand if you might need a second look to get the idea. Okay? But let me come back to the point. The point is that the notion of reduction simply means that we are going to transform one problem into a more general problem. Okay? Now, why? Now, let me come back to the NP-complete. So what it means is that the NP-complete problems are the most general problems because you can reduce all the other problems in NP to one of the NP-complete problems. They are the most general ones. So if you know the solution to any one of them, you know the solution to all of them. Okay? That's the notion of NP-complete. Now I'm going to come to the very last class of problems, and that is called NP-hard. Okay? Now NP-hard problems are essentially problems that is at least as hard as NP-complete problems, and they may not even be verifiable. Okay, now what is an example of that? An example of that is exactly the traveling salesman problem. Now, what does it mean to be verifiable? It means that I can propose a solution and you can check whether the solution is correct or not. Now, suppose that we have a problem of traveling salesman. There are 100 cities that we need to visit, and let me propose a solution. And I say that we go to city 1, and then 2, and then 3, and then 4, all the way to 100, right? Now, can you check for me whether that is indeed the correct solution? So for that to be the correct solution, it must be the tour that has the shortest distance. So how do you know whether that is going to be the one with the shortest distance? You have no way of knowing other than actually solving the problem. So which means that even the verification is also n factorial. Now, those kind of problems are what we call NP-hard problems. Okay? Now, the general understanding today is that we look at a problem, and if we can show that our problem is NP-hard, what it means is that we should find another problem because they are too hard. Okay? So which means that if you design an algorithm or you encounter a problem and you can show that your problem itself is NP-hard, then you will go on and find a different solution, a different problem. You will reorientate it, you will reframe it into a different problem that you can actually solve, usually using part of the heuristics. Okay? Now, so when you look up textbooks on algorithms, you will encounter these 4 classes, which is what I call P, NP, NP-complete, and NP-hard. Okay? And they have different significance. So if a problem is in P, means solvable, it means that you can use it. So go ahead and implement it, you're going to solve the problem. Okay? Now, if your problem is in NP, now it may or may not be solvable, but you can check. So which means that there are some ways that you can solve the problems. For example, you can try random solutions. And then you can check whether you get a solution or not. Now, if your problem is in NP-complete, it generally means that it's still too hard. Okay? And at this point of time, we don't yet find a solution to any of the NP-complete problems. Now, if your problem is NP-hard, go away. Find another problem, reframe it, such that it becomes like an approximation or heuristic. Okay? Now, one last thing is, it is not known yet whether P is equal to NP. So the idea is that, is it true that all problems that are verifiable are also solvable? So we don't know that yet. Okay? If you know, you're going to get $1 million. Okay? It's one of the Millennium Prize problems. If you solve any one of them, you get $1 million. Okay? Now, why is this important? Now, let's look at the 2 scenarios. Right? Now, this is a scenario that most people believe today, that P is not NP, meaning that there are problems that are in P, and then there are problems that are in NP that is not in P, meaning that there are still problems that are verifiable but not solvable. Now, then this is going to be the picture that you have. So P is going to be a subset of NP, and NP-complete is going to be the hardest problems in NP. These are problems that we don't know how to solve yet. But remember that if you solve any one of them, you solve all of NP. Okay? If you solve any problem here, you're going to solve all of NP. Then we have the NP-hard, which is outside of the NP, meaning that they are essentially at least as hard as the NP-complete problems. Now, if P is equal to NP, then essentially the whole picture is going to be like this. Essentially, P, NP, and NP-complete are the same set, which means that you can solve any problem that is in NP. As long as you can verify it, you can be solved. Okay? Now, this is both a good thing and a bad thing. Okay? If indeed it is true, the good thing is, it means that a lot of problems that we now think are unsolvable actually can be solved. Okay? Now, if it is true, there is also a bad thing. Okay? Now, because there are some technologies that we have today that are based on the idea that P is not equal to NP. Now, one example of that is the cryptography in security. And the idea of cryptography in the security is that they have this public key and private key, right? It's based on the prime prime number factorization. So it's easy for us to multiply. It's very difficult to factorize. Now, for someone to break into the security, they have to be able to do the prime factorization. Now, and because at this point of time we believe that is an NP-complete problem, it cannot be done yet. Okay, but if it can be shown that it can be done, then all the securities will be broken. Then we have to invent a whole new way of doing security in the internet. Okay, now this is the last thing we will learn in CT. Okay?
Yes.
Okay, so no tutorial for this one. Just make sure that you understand the concepts P, NP, NP hard, NP complete. Okay? Now, I'm actually also going to stop here. Okay?